Hello everyone. So in this video we will be doing another diagnostic test for this video series. Today it will be about functions. Some information you can obtain about functions, sketching functions, and things of this nature. So to start, we will look at a very important concept that will come up later in calculus. And right now, we just want to evaluate the following. So given the function f of x is equal to x cubed, find f of 2 plus h minus f of 2 divided by h. This quotient will show up very often in calculus, especially when discussing limits. But for now, we just consider h any variable that we'd like. So, for us, we simply plug in each of these values in the numerator, and we evaluate the quotient. So, doing so, we find that we plug in 2 plus h cubed minus 2 cubed divided by h. Now this is equal to, well, first we cube this 2 plus h. So we write out 2 plus h times h squared plus 4h plus 4 minus 2 cubed, which is 8. This is all divided by h. Then we factor this out once more, or we expand this out once more, and we get h cubed plus 4h squared plus 4h plus 2h squared plus 8h plus 8 minus 8 divided by h. So immediately we see that these 8's cancel, and we can combine some terms. Moreover, each of the remaining terms all have an h in them, as the two 8 terms here, which had no h's, canceled. So we can further cancel this h with one h from each term. So the h squareds become h's, the terms with just h's become a term with no h's, and the h cubed term becomes h squared. So in the end, this quotient is simply written as h squared plus 6h plus 12. Next, in order to follow along with this series, you should be able to find the domain, so the domain of the following functions. Consider the function f of x is equal to 2x plus 1 divided by x squared plus x minus 2. Well, the domain occurs whenever a function is well defined. So for a quotient like this would be whenever the denominator is not equal to 0. So we would like to find when the denominator is equal to 0, and hopefully from there we'll find some values which will give us a good range on the domain. So we say we want x squared plus x minus 2 equal to 0. Well, we could use the quadratic formula, or we can notice that this can be factored into the product x plus 2 times x minus 1. Then this is equal to 0 when x is equal to 1 or negative 2. So the domain here, the domain of f is equal to negative infinity, open bracket, because we can't contain negative infinity in our domain, going all the way to negative 2. But because the denominator is 0 at negative 2, that's also an open bracket. And then we also contain, so this symbol here means or the union of this interval with the preceding interval. We go from, well, we can contain all of the space from negative 2 to 1, so long as we don't contain negative 1 and 2 themselves. So we then take yet another union with the interval from 1 to infinity. So we notice that the domain of f here is all real numbers without negative 2 and 1. Next, consider the function given by g of x is equal to the cube root of x divided by x squared plus 1. Well, again, the domain of g occurs whenever this is not well defined. The numerator is always well defined because it's a cube root, so even if you put a negative, it's okay because it's not a square root, it's a cube root. And this here, x squared plus 1, well, if we wanted x squared plus 1 is equal to 0, this would mean that x squared is equal to negative 1, which would give us solutions of x is equal to plus or minus I, where I is the imaginary number. And because we're not defining domains in the complex plane, we say that this is also never equal to 0. So the domain of g is equal to the entire number line. So all real numbers are within the domain of g and are the domain of g. Finally, consider the function h of x is equal to square root 4 minus x plus the square root of x squared minus 1. Here, we find that there are no denominators because there are no quotients. So naively, one might expect that this is always well defined. But because we're doing analysis in the real plane, we are only dealing with real numbers. So we are not allowed to have negative numbers inside of these square roots. And you may notice there are certain values of x so that what's inside of the radical becomes negative. For example, if we choose x is equal to 5, then we get square root minus 1, which is not a real number. So that's not allowed. And therefore we have some limit on the domain, even though we no longer have quotients. So we know already that we cannot have 5 or any number greater than 4, because if there were an x greater than 4, this would be negative. So we know there's a hard cutoff at x is equal to 4 for the domain. So whatever our domain is, we certainly have a hard bracket here with 4, and there's nothing else. Moreover, if there were a number, say, we chose here, we chose x is equal to 0.1, then x squared is equal to 0.01, and the radical becomes square root of 0.01 minus 1, which is a negative number inside the radical, and it becomes imaginary. So again, this is not allowed. So we already know that the absolute value of x, or the value of x, cannot be between 1 and negative 1. Because if it were, then this would become negative. Other than that, there are no restrictions. So we know we can go anywhere from 1 to 4. Those are all allowed values of the domain. So we're looking at the domain of H. Negative infinity is also allowed. That's a perfectly allowed value. Or any arbitrarily large negative number. All the way up until and including negative 1. So we say negative infinity up until and including negative 1. And we include negative 1 here. We include negative 1 because, well, the first term is fine with it. It doesn't become negative under the radical. And the second term of h, we're squaring x anyways. So it doesn't matter if x is positive 1 or negative 1. They both are 0 because it's x squared minus 1. But none of the values between negative 1 and 1 are allowed. If you choose any of them, then the second term becomes imaginary, and we're not allowing that. So this here, the union of these two intervals, is the entire domain of H. Moving forward, we'd like to make now some sketches. So we just covered domains of functions. Now let's find rough sketches of functions. So this is a very useful skill later on in calculus to visualize the functions that you'll be working with, and it's also a skill that's useful in math and physics more generally. So the more you start to work with these sorts of functions, the better intuition you'll have for them. But you should already have some intuition before going into this video series. So to start, I will just begin naming some functions and drawing their plots. Another great resource for this, outside of the subpar drawings that I'll be providing, is a website called Desmos. And it's just a free plotting website where you can plug in a function and plot it. There are also countless others online that you can use for free. But let's consider y is equal to x cubed. Y equal to x cubed is a relatively simple plot. So for us, that would just look like the blue plot I'm drawing here. So it comes in, flattens out at 0, goes to positive infinity for x large, and it goes to negative infinity for x being negative. Next, let's consider the plot of y equal to x plus 1 cubed. So this is going to act just like x cubed, except there's now a horizontal shift in the plot. And the way to see this is to see that there's a unique value for which y is equal to 0. Here, it's when x is equal to 0. Now, y is equal to 0 occurs when x is equal to -1. So, the part up here where x was 0 has to shift to x is equal to -1, or it has to shift to the left. So, for us, that would mean that the plot, if this is -1 now, simply looks something like this. So it's the same plot as before, except shifted over. Considering some other plots, just to cover a variety of them, if we were to add, say, a shift to what I just drew above, so say y is equal to x minus 2 cubed plus 3. So whereas we had x plus 1, that shifted it to the left, x minus 2 will shift it to the right. And that's because the new 0 value is that x is equal to 2. But in addition, we have a constant shift to the y value, which is 3. So for us, the new value where it flattens out here occurs 2 over, so 1, 2. It occurs at this x value, and it occurs at the y value of 3. So we go up 3 units, and the plot should look something like this. Next, and almost finally, we have y is equal to 4 minus x squared. This plot is, well, we see a parabola here, which is what the second term is. So a parabola normally looks like this, except now we have a negative sign out front, so it's going to be flipped. So it's going to be reverse of this, rotated 180 degrees. So it's going to look like this. But there's a constant y shift of 4, so it's going to be what I just drew, translated up 4 units on the y-axis. So this value here is 4. And finally, another important function that we'll be working with is y is equal to the square root of x. So this function is interesting to plot because whereas before we could define our plots everywhere, this function is not defined everywhere. So for us, we are not allowing negative values of x. So automatically, none of these values are allowed. Furthermore, the square root of x is never negative, it's always positive, and it grows like this, where it achieves a 0 value at x is equal to 0. Anywhere else on the plot, so any negative x value, it is not defined. And the last topic I want to look at is, in this video, is function composition. So function composition will show up repeatedly in calculus as well. So given the functions f of x is equal to x squared plus 2x minus 1, and g of x is equal to 2x minus 3, we'd like to consider the following. Firstly, what is f composed with g? Well, the way that you would want to write this out is that f composed with g is really just f of g of x. So we know what g of x is, and it's given by 2x minus 3. So everywhere we see an x in f of x, we put 2x minus 3. That's the way function composition works. So here, that would mean this composition is equal to 2x minus 3 squared, because it's x squared, and x here is really g of x, plus 2 times 2x minus 3 minus 1. Then, expanding this out, this becomes 4x squared minus 12x plus 9. So that's the first term here, plus 4x minus 6 minus 1. Now, simplifying this, we get 4x squared minus 8x plus 2. So that is the composition that is f composed with g. Next, we can consider what is g composed with f. Well, just like before, g composed with f is g of f of x. So we see what g of x is, and everywhere we see an x here in g of x, we put x squared plus 2x minus 1. So we have 2 of x squared plus 2x minus 1 minus 3. And expanding this out, we get 2x squared plus 4x minus 2 minus 3. So this just becomes minus 5, and that is the function composition. Finally, we can consider a weird one, which would be, let's say, g of g of g. So this is really g of g of g of x. And we can write this out perfectly fine. So we begin one step at a time. Let's first do the inside. What is g of x? Well, you take 2x minus 3. Everywhere you see an x, you put 2x minus 3. So we have 2 times 2x minus 3 minus 3. This is 4x minus 6 minus 3, so minus 9. Then this is the x value that we use for the next g of x. So this function is 2 of 4x minus 9 minus 3, which is equal to 8x minus 18 minus 3. 18 minus 3. 18 minus 3 is 21. So this becomes 8x minus 21. And that is function composition in some detail. In the next video, we'll be discussing trigonometry, and that will be the last diagnostic test before we get into actual calculus material.